Hi everyone, welcome to our Diana e-learning session of today. My name is Jean-Claude Boruel and I will be hosting this session. In today's webinar, we are going to discuss some general information about pile analysis and pile modeling in Diana. And as usual, for the one who are already familiar with our e-learning session, we will have a live demo after this short presentation. So let's start. Let's start with a statement from Das. Also, numerous investigations, both theoretical and experimental, have been conducted in the past to predict the behavior and the load-bearing capacity of piles. The mechanisms are not yet fully understood and may never be. Of course, from the structural point of view, piles are not that complex, but their interaction and the soil around them are usually with a lot of uncertainties, and the behavior is always unknown. So each case can be an independent case. And there are things in the interaction that people are still looking after, and research is going on pile analysis and pile foundation. In terms of terminology, if you travel from one country to the other, the terminology may differ. Deep foundation is known as a long slender with structural members consisting of steel, concrete, wood, plastic, or a combination of these materials. Piles in Europe means in general pile foundation, when in US it refers to driven piles. Drill shaft in US are called bored piles in Europe and other countries. We have also displacement piles due to driving of the piles, the small displacement piles that displace a small volume of soil relative to external volume, and the non-displacement piles mainly installed by excavating the soil. When to use deep foundation? If you have a soft soil near the ground surface and it's not able to carry your load, for instance, if you have uplift forces, the same goes for problematic soil, collapsible or expansive soil near the ground surface. If you have large lateral load and you need to carry this load by your foundation, if you have tilting or risk or screw effects, like foundation for bridge in waterways, stability risk, foundation near excavation of or slope, or if you have heavy loads that cannot be carried by traditional rough foundation, for instance. Deep foundation can be classified by material, by method of installation, or by effect of installation. In terms of material classification, we have steel piles, concrete piles, mostly common use, and timber piles. In terms of installation method, we have driven piles, drill piles, and screwed piles. And regarding the effect of installation, you have the displacement pile, the small displacement piles, and the non-displacement piles. Let's have a look at the load transfer mechanism of the pile. So on this sketch, you on the left side you have a pile of a length L with the pile head, the pile base, or pile tip. The diameter of this pile is B, and here is a pile shaft, the skin. When we load the pile on the top, let's say, loads are transmitted mainly by two things: the shaft friction along the skin of the pile and through the base of the pile, near the pile tip. The pile can be designed to be a shaft or a frictional pile without any bearing resistance. It can be a fully end-bearing pile or a combination of both. It depends on the soil condition and the pile itself in terms of size, length, and also depending on the load. Usually, piles are used in pile groups. Only in pile testing, you use a single pile. They are connected near the pile top by a pile cap. The design will involve determining the optimized design for the number of piles, the spacing, the layout of the piles within the pile foundation. The pile cap mainly serves to distribute the load coming from the top to the different piles and to connect these piles to the upper structure. The ultimate capacity of piles may not be equal to the number of piles multiplied by the capacity of a single pile. The ratio of the pile group capacity to the total load capacity of the piles acting as single piles is called the group efficiency factor. This factor depends on, among others, on the number of pile rows, number of pile over the rows, the spacing and diameter of the piles in the group. Next to pile group, we have pile raft. Pile raft foundation provide an economical foundation option for circumstances where the performance of the raft alone does not satisfy the design requirements. Under this situation, the addition of a limited number of piles may improve the ultimate load capacity, the settlement and differential settlement performance, and the required thickness of the raft. This is a statement from Poulos. In terms of advantages, pile raft foundation, for the pile raft foundation, limitation of absolute settlement and differential settlement, it's one of the advantage. The reduction in foundation tilting, either due to load eccentricity or due to irregularities in the subsoils, and the reduction in raft internal stresses. The main objective of pile group design is to ensure that the foundation does not undergo excessive displacement. So that's what we call the serviceability limit state, or SLS. Additionally, often a factor of safety against collapse of the pile is required, and that's what we call the ultimate limit state, or ULS. According to Randolph, for most applications, the real ultimate limit state must be determined by considering the interaction of foundation and superstructure. The ULS then reverts to a displacement criterion that is determined by structural considerations. If we take a closer look to the bearing behavior of pile raft, on the left side, basically you have a sketch where the raft is disconnected from the pile for some more clarity. And on the right, basically we have some arrows displaying the different interaction that are governing how the pile raft are performed. These interaction are basically four interaction: the pile soil interaction, the soil raft interaction, the raft pile interaction, and the pile to pile interaction. So these four interactions are governing how the pile raft perform. The total bearing capacity of the pile raft is the summation of the bearing capacity of the pile and the bearing capacity of the raft. This is the Q tot. The bearing capacity of the pile, QP, is the base capacity. The base capacity plus the shaft capacity, QS. The bearing capacity of the raft is the contact stress over the area of the raft. And the total capacity, the total bearing capacity of the raft should be larger than the applied load time a factor of safety. If we look at the behavior of a single pile versus a pile group and a pile raft, on the graph on the right side, you can see in black the behavior of the single pile, in green the pile group, and red the pile raft. It is clear that pile group behavior and pile raft interaction reduce on the one end the stiffness of the piles and increase on the other end their bearing capacity. In terms of requirement for the design of pile raft, the serviceability limit state is a decisive criterion for the design of vertically loaded pile raft. The magnitude of absolute and differential settlements and tilting of the building are therefore of special importance, especially for high-rise building. The question arising in the design of pile raft are the relative proportion of load carried by raft and piles, which pile configuration, in terms of number of pile lengths and layout, reduces absolute and differential settlements and structural force most efficiently. To answer this question, three-dimensional finite element analysis is very well suited, and that's what we are going to discuss further, and we will also show you in the live demo. The requirement for a realistic numerical model. The model should be able to consider the three-dimensional behavior of a pile raft foundation. The applied constitutive laws should be able to take into account the nonlinear pile soil behavior at pile shaft and pile base. The stress-strain behavior of the soil depends on the applied stress path and strain level. Therefore, the applied model should be able to take this effect into account. The model should be able to simulate the behavior of a single pile to check its reliability and to adjust the applied parameter depending on the chosen pile type. So you should be able to carry a kind of calibration on this pile. The applied model should be able to consider the different interactions that govern the behavior of pile raft. The workflow to model a pile raft foundation would start by creating a numerical model and feeding it with input parameters coming from geotechnical tests, whether from lab, field test, or from single pile test. At this stage, a calibration process is possible. So basically, you would start with a single pile test model that you would calibrate and then go for the full model. Then you perform your analysis and you get your force displacement diagram. Again, at this stage, you should be able to do a parametric study or change some load combination. And rerun some analysis. So it's an iterative process. At the end, you get structural parameters that can be used by the structural design engineer. And again, this part is an iterative process. I mean, it should be a discussion with the structural design engineer. And based on this feedback, you may need to rerun some simulation. So this is the general workflow. Coming back to Diana itself, through the time we have implemented different approaches for pile modeling. We have three approaches basically available: the solid element model, the beam solid connectivity model, and the pile foundation or embedded piles with line to solid interface model. In the solid element model, the soil and the pile are both modeled with a solid element, and the connection between soil and the pile is modeled with interface, surface interface element. For this type of approach, you need to have a nodal connectivity on the pile outer surface. The model definition and the mesh generation could be elaborated when you have a large number of piles. And it leads also to many elements in your model, leading to a larger computational times. The beam solid connectivity model consists in modeling the soil with solid element, and the pile with beam elements. The interface between the solid and pile is then modeled with beam solid interface. A nodal connectivity is required along the pile length. The nodal compatibility requirement makes geometry modeling and meshing of the soil elaborative. And for pile raft with large number of piles, this technique produces large model and leads also to large computational time. Finally, the pile foundation or embedded pile approach consists of modeling the soil with solid element again, But then the pile is modeled with embedded truss or beam elements, and the interface between the soil and the pile with line to solid interface elements. These interfaces are generated automatically. For this approach, you do not need to have nodal connectivity. Piles and soil geometries and meshes can be specified independently. Intersection of lines and solid elements are automatically calculated. Nonlinear friction slip properties for line solid interface element can be specified. The mesh requirement for the soil is minimum, leading to a reduced computation time. So this approach is very well suited for pile graft foundation. And this is the approach that we will show and demonstrate during the live demo. Next to that, for the pile foundation, we are developing a pile wizard in DynaAI for the last approach. With this pile wizard, with this dialog box, in one go, you have access to all the required parameters in terms of material and geometry properties. And once you have defined this property set, you can simply drag and drop your pile's geometry line in terms of lines into this pile set. Then they automatically get assigned pile properties, and it's very intuitive and very easy. And I will show you in more detail during the demo how we proceed. But it's a very intuitive procedure. In terms of input parameters, these interfaces, pile-soil interface, are characterized by a few parameters: the ultimate shear force, which is your limit, the shear stiffness modulus Ks, which is basically the slope of your graph here, and the normal stiffness of the interface in the normal direction. The pile bearing capacity is an input. This is important in pile elements. It's not a result, it's an input, so you have to specify it. If we look more closely to this interface between pile and soil, they could be represented as every interface could be represented as a set of spring, where you have a normal one and the actual one. So a spring with the normal stiffness Kn in the normal direction, and along the actual direction, a spring with a stiffness Ks, the shear stiffness. The traction that are related to this stiffness are Ts and Tn. The same goes for the tip bearing capacity, which can be seen as a spring with a stiffness Kb, and basically the base bearing capacity is Qb. Because of the large number of interface, so the large number of springs, there is a high interaction of all these springs, so we end up having a highly nonlinear curve describing the force displacement of a single pile. And next to this property, we have also the pile beam properties, pile truss properties, in terms of cross-section property, the length, and the material properties, concrete or steel. For this embedded approach, we did a validation when it was introduced in Diana, so already some time ago. It's from a study from '99. It's a single pile analysis of the Halsey Bridge pile loading test. And from which we get some measurement and some data. And we could achieve some reasonable way, or capture in a reasonable way, the behavior of the individual component. Here on one graph, you have the measurement and the Diana results. And you could see that we can catch the behavior, the three behavior for the skin friction, the base tip, and the total bearing capacity quite well. So, having said that, let's move to the live demo. Here is an overview of the model that we are going to make today. It's a 3D model consisting of a bridge pier in blue, which is resting on 12 piles of diameter 0.7 meter, and 3 layers of soil, respectively of 6, 5, and 18 meter thickness. The piles will be defined in 2 sets. Basically, we'll have a set of pile for the pile inside the pier foundation, and another set for the pile into the soil, inside the soil. We will use the embedded pile element concept as we discussed before, which will lead to the automatic generation or creation of the frictional shaft and pile tip behavior. The bridge pier deck will be loaded on the right and left side with unsymmetric loading to have a kind of tilting effect. The dead weight will be automatically considered in the construction stage that we will perform. When you use the construction stage, you don't need to model explicitly the dead weight. It's automatically created and automatically considered, so nothing to worry about. During this analysis, we will consider 3 stages. First, the initialization, where only the 3 soil layers are active. Then we will add the piles and the bridge pier, and finally we will apply the deck load. In this table, the properties of the soil layers and the piles are listed. For the 3 soil layers, we will use a more coulometric model. And for the pile, we will assign elastic concrete material properties. And as I mentioned before, all the pile will have the same diameter, 0.7. For the pile foundation interface, we will also use some property. Here are the different stiffness for the shear and normal behavior on the ultimate shear force per length. Here are the property of the pile soil interface, and we will input that through our pile wizard. I will show you. And finally, the property of the pile tip interface. So let's move to the presentation. To the live demo. Let's get back to Daniela. Here we go. So first we need to start a new project. I'm going to call it Bridge Pier Demo. I'm going to use one of my working directory. Okay, my documents, fine. So for this model, we choose a structural analysis. We go for a 3D model. The model size, we keep it 1 kilometer. As you know now, I mean, it's a dimension of the box in which your model should fit. And I keep the measure type to hexaquad, and I keep things linear. In terms of units, we are going to use meter, ton, sorry, kilonewton, second, Celsius, and degree. Always use a consistent set of units before to start your model. Although you can change the units interactively, it's always good to know in which units you are working. So we can now start the modeling. The way I'm going to proceed, I will first model the top surface of the topsoil layer. Then I will extrude this surface in the Z direction, downwards, and this will create my first soil layer. Then I will extract the bottom face of this soil layer, extrude it again. This will create my second soil layer, and I will repeat the same procedure for the third soil layer. So to do that, I first need to create a surface, but I'm going to call layer 1, starting in a position 0, 0, and my layer will have a dimension of 120 by 120. I click create. Here it is. And then I extrude this face in the Z direction, and it's 6 meter thick. Apply. And here under shape, you see that you have the first layer. Next, I'm going to select the bottom face here. First, I need to close the extrusion. So the face is selected. Right click, go to modify, and I extract this face. So now you see that I have it here. I can rename it to layer 2. The renaming, you can do it at any stage. And then I repeat the extrusion operation. So I select this face, and now I go for 5 meter extrusion downwards. Apply. So here is my second layer. And I'm going to repeat the same operation. So I select, first I close this, I select the bottom face, I right click, go to modify and call extract. Then the sheet 2 is created. I'm going to rename it to layer 3. Rename. Okay. And I'm going to extrude it. And this time it will be minus 18 meter. So we have our 3 solid layers. We can eventually choose a different color. So here are 3 solid layers. Now we need to model the pier, and I will start with the pier foundation. So I will create a block. I call it foundation. And I specify the dimension. And I click create. So here you can see my the foundation of the pier. Next, I need to define the pier itself. So for that, I have already prepared an Excel sheet in which I place all the point coordinate to facilitate this like demo. And I'm going to define a sheet, but this time I'm going to use the coordinate option that I copy. And I'm going to call it pier. And here you can see the section of my pier. I need now to extrude this pier section. In the Y direction with 2.3 meter. So I have the foundation and I have the pier. Since we will assign concrete property, I'm going to make them gray. Something a little bit lighter eventually, so that you can see it better. So we have defined the 3 solid layers. We have defined the foundation of the pier and the pier itself. Next to that, we need to create some line geometry for the pile. So what I'm going to do, I'm going first to model one pile, and then using the array copy tools of Dynai, I will get the rest of the piles. So first I create one line. So 65, I'm going to enter the starting point. and the endpoint. So I have files of 11 meters long. I create, so that you can see something. I'm going to hide the 3 layer, and you see that I have one file which is created. So as I said, to create the other files, we are going to use array copy. So I select the file, and first I'm going to copy in the Y direction with an offset of 1.43 meter, and I do it 2 times. So immediately see the preview option of this copied action. Click apply, and it results in 2 extra piles under the shade tree. We repeat the same action. Now I select my 3 lines, and I'm going to copy them in the X direction with an offset of 3.45 meter, and I'm going to do that only 1 time. Apply, and then you see that if I expand a little bit my window, you see that I have my 6 line. Finally, we copy all these lines, and again in the X direction, but this time with an offset of 6.762 meter. Only 1. Click apply, close, and we have our 12 piles. So it's very intuitive, very easy to create this geometry. For the ease of use, I have defined a pier and a foundation. I'm going to merge these two to have only one entity. I'm going to use the unite option. So my target will be Pier, and the tool will be foundation. You can interactively, whether you select from the geometry tree or directly from the window, it's really up to you and your preferred way. I know that myself, I usually do both. So, and for the operation, I click on unite, I choose unite, and I click apply, and you see that now I have only one entity, one set, one shape, which is a pier. So if I show everything, our geometry is pretty advanced. We have our 3 layers, the pier, and the 12 piles. As you probably remember, when I was presenting the model, I said that we are going to use 2 sets of piles. One set for the piles into the concrete foundation, and one set of embedded piles for the part inside the soil layer. So it means that we have to split these piles. To do that, I first need to get an imprint of the connection between the foundation and the pile. So to do that, I go to imprint shape, and for the target, I select the 12 piles, and for the tool, I choose a pier, and I say imprint. Apply. And now if I hide the pier, I zoom in, you see that there are some pink point at the edge of the bottom of the foundation. So this is the result of our imprint. It means that now if I use the break function, I will split the piles at this level. And that's exactly what we are going to do now. So I select the piles. First I close this, right click, modify, and go for a break. And you will see under the geometry tree on the left that it will result for every line in 2 parts. go for break. If I extend that, you see now that for every line, I have two parts, part 1 and part 2. The part 1 is a part within the concrete, and the part 2 is a part within the soil. So let's move now to the property assignment. Before to start the property assignment, I'm going to import some material so that I don't have to type all this value again. So these are the model, the material model we are going to use. I can quickly go through. So for the topsoil, these are the different value and the more Coulomb model which were specified in my table. So we have a topsoil, the mid-soil for the layer 2, with the linear property, the more Coulomb, and the initial stress. And the same for the last soil layers, bottom one, linear property, cohesion, and the initial stress. The linear elastic concrete for the pile. So all these values, you find them in the presentation in the table. And the pile in soil and pile in concrete, I will show you them through the pile wizard. But these are basically the set of property for the pile itself, and also the interface and the pile tip. So first, let me start with assigning the property to the Pier, structural, concrete. Then I go to the first soil layer. I need to select. Here we go. So I go for topsoil. Repeat the same operation for the second soil layer. And finally, for the bottom soil layer, or layer 3. Okay. So I can hide this 3 layer and the pier as well. And now I'm going to deal with the pile. So, as I mentioned during my presentation, we have a pile wizard for that. I'm going to expand it a little bit. And how it works. So first, you create a set, and I'm going to make 2 sets. So pile in concrete and pile in soil. And I'm going to upload the existing material, so my pile in concrete that I imported. And you can see here that I have all the properties that were in my table, basically. So the pile properties, the pile shaft to soil interface properties with their stiffness in normal and shear direction, and the ultimate force. And for the geometry of the pile, I'm going to define 1 set. Which will be circular pipe shape, a diameter of 0.7. The orientation will be along the x-axis, and the surface area will be 0.38465. And its actual. So this is it for this set I create. Then it results in a pile in concrete set under the geometry. And what I need to do is just to select the part 1 of every pile. Let me expand it. So all the part 1 is selected, whether you do it from the working window for the tree, doesn't really matter. And then you drag them to the set. And automatically, this part gets assigned the pile in concrete property. in terms of material and geometry. So very easy. I mean, in two actions, you define your first action is you create your set with all the property, and the second one you just drag the geometry entities to this set. So we can repeat this operation for the pile in soil. So this one we allow bending. I'm going to load the pile in soil property, for which we have activated the pile tip. So it means that next to the pile property and the pile shaft to soil interface property, we have also pile tip to soil interface property and the pile tip resistant force. So all these input value are available in one window. And for the geometry, we have the same dimension, same diameter, so we use the pile. And you create the set. So you end up with a second set, which is pile in solid, and then you select all the part 2 of your piles, and you move them to the pile in soil, and then you have your two sets, pile in concrete and pile in soil. So the workflow is really straightforward and very intuitive. So we have created our pile. We have our 3 soil layers, the pier. Next, we are going to define the load. So as I mentioned, the self-weight, you don't need to model it because since we are going to use a stage construction analysis, this is automatically done. So there's no action required on that side. We simply need to model the deck load. So I will start with the right pressure, which will be part of a set pressure, face, no, not this one, and zoom in so that you can see. So I select the right one, and here I'm going to apply minus 2000 kilonewton in the Z direction. Click create, and I repeat the same for the left side. Net pressure, and here I'm going to apply 3000 in the downward Z direction. So we have assigned our load. Now we need to set some boundary condition. So I start with the X direction. So I select the edge of the model that should be constrained in X. This is it. Then I do the same for the Y direction. But then in Y. And finally, I will support the bottom of the model in the Z direction. So I think we are pretty complete now for the model. We have defined all the geometry part, the pile. We have assigned properties to the different part of the model. We have defined our deck load, and we have assigned boundary condition. So we can move to the mesh building part, which is the last stage before meshing. So here I want to assign some element size to the pier, and I go for 1 meter. If I click on preview, you can see the mesh sealing, and you can see also some arrows. These arrows are basically giving you the orientation of every edge. This is quite convenient when you need to specify a grading, and you need to know the start and ending point of the edge. So I click apply. Next, I'm going to specify some seedings for the vertical edge of the model. So I go for edge, and I'm going to specify division. I want to have 8 division, and I'm going to select all the edge, all the vertical edge. You can see that for every edge there are 8 division. I click apply. And finally, I am going to assign a general division to the body of the 3-cell layer. Please note that hierarchy for the seeds are from edge to face and from face to shape. So if there is any assigned seed to the edge, they govern the face or shape assignment. So what I'm going to specify now is not going to affect the edge seedings. So I go for shape, division, I go for 8, and I select my 3 layer. So you see that the vertical edge kept this 8 division, and now this edge have 8 as well. Apply. And now I can click on mesh. And this is the mesh of our model. We can hide one of the cell layer, and we can zoom in so that we can see the pile which are nicely going through the soil. Having said that, now we need to set up our model. So we go to the analysis, and we are going to use a construction stage analysis. For which I'm going to define 3 phases. The first phase is initialization. In this phase, basically, I don't have any water, I initialize the stress, all the soil layers are active, and the concrete pile and pier, the pile and pier are not there. So only the 3 soil layers are active. I'm going to duplicate this phase, and I call it pier and piles. I don't need to activate that, and then the pier and the pile get active. And finally, in the last phase that I'm going to call deck loading, I just need to add the load, which is my pressure load. And all the parts of my model are active. So if I summarize, first, initialization phase, where only the 3 soil layers are available, and we go for stress initialization. Second phase, we activate the pier and the pile. And last phase, we add the deck load. So I can start this analysis, but I've already run the analysis to save time. Get back to this one. Because it takes less than a minute, but to save time, I already prepared the results. So let's see what we can show from this analysis, starting with the vertical stresses from the stress initialization, so SZ. You can see that we have uniform layer, so nice distribution. If we now look to the next phase, where we place the pier on the pile, and we can look at the displacement. So this is the pier on the pile, only with the dead weight. And if I go for the deform, you can see that it's moving down nicely. If I go to the next phase, where I load the deck with a an unsymmetric load from the right to left, and I go for deform, you can see the tilting of the bending of the pier nicely. I can show you some pile results if I add the Swisser layer. And I go for some pile results. I can show you the pile cross-section in terms of diagrams. I can orient them. If I go to the results, you have a lot of settings for the results, so you can really play with that and present things the way you want. What I wanted to do was to change this to global X, so you can see the cross-section forces of every pile. We can also present the bending moment. So you can see how nicely it bends the pile. And finally, I can show you some pile tip results. The pile tip cross-section, NX show contour. And you see that they are represented as sphere. And what we can see is that we reach minus 349. So we don't reach the ultimate force of 500. We are still on the safe side for this one. So this is it for today e-learning session. So we went through a short presentation with some general information about the pile raft modeling and analysis. And we did together the modeling of a bridge pier supporting on piles. And you could see how easy you can define and assign property to your pile thanks to the pile wizard we have in Dyna.IE. And we also perform a stage construction to look at some results. So I'd like to thank you one more time for attending this e-learning sessions.